Hi, welcome back to AP Physics 1. This is Unit 2. Again, we're talking about dynamics. And this is our last video for the unit. This is circular motion. So this particular topic used to have its own unit prior to 2024. This used to go with the gravitational force video a couple videos ago. So these are stuck together in one single unit. But now with the influx or the addition of fluids and the splitting of the rotation unit, they had a little wiggle room, and they decided to put circular motion into unit 2 because this is just really an extension of Newton's laws. Okay, so the way we look at it, you got centripetal acceleration. So remember, anytime an object is either changing its speed or changing its direction, it will accelerate. Okay, and so what's happening here, this is when you have the constant velocity with the changing of motion or changing of an object's direction. So what we say is that there's a centripetal acceleration. It's the component of an object's acceleration directed toward the center of the path. Okay, in fact, centripetal means center seeking, right? And the magnitude of that is given by the equation A sub c equals v squared over r. Okay, where v is actually the linear speed and r is the radius of the circle. So every turn you take in a car or in anything is part of a circle, right? It could be like a real short turn, but that's still part of a bigger circle. Now, because centripetal acceleration can result from a single force, more than one force or components, so the acceleration, it's kind of weird how I just worded that, but the acceleration can result from a single force, right? More than one force or components of forces exerted on an object in circular motion. Some of the common forces would be like friction, tension, normal force. So you see that here in the roller coaster would be a normal force scenario. So this means that the centripetal force, because remember, anytime we accelerate, we have a force associated with it. That just means that anytime that the centripetal force is not going to be a force itself, but it is going to be the net resulting force. And so if you were to do a free body diagram, right? So the centripetal force is mv squared over r, right? Because a or F is equal to m times a, then a sub c in circular motion is v squared over r. So if we think about this car, right? This is my weekend car, just saying, right? But if I do the free body diagram on it, you would have the normal force because we have the surfaces interacting. You would have the car's weight. And when it takes a turn, you would have friction going inside. Okay. Now, typically what we will talk about, splitting up the horizontal and vertical. The way I like to split these up is circular and non-circular. So the way this works out is these two forces are your non-circular forces. These have nothing to do with the actual turning of the car. And then in this case, the frictional force is actually the force that causes the turning, right? So this ends up being the net force for the car, okay? And then when you get into a scenario with the roller coaster, if we look at it, we have FG down, you have F normal up, because that's actually what keeps you, in fact, normal is not up in this scenario. Normal is actually going to be pointing down because it's where you're in contact with the surface of the seat, okay? And so in this case, these would be your circular forces. Oh, sorry, right, forgot about it. So friction is your circular force. Okay, these two are your circular forces, and there are no non-circular forces in that problem. Okay, so if you were to sum the forces for our car, you would get F equals F sub c, and you end up with mu Fn equals mv squared over r. And so then you just solve. Like you be asked for the coefficient of friction between the tires and the road. You be asked to find the speed at which you can take the turn or the radius at which you can take the turn. But one thing interesting happens, right? It's because mu mg equals mv squared over r. And then if I cancel out the mass because it's the same car, you see this mu g, right? This is just telling us that the sliding acceleration of a car is just simply, that is the proof that that is the only force that's causing acceleration. Okay, now something that you may also have to deal with is, how fast is something moving in that circle? So you have the revolution of an object traveling in a circular path at a constant speed, which we call uniform circular motion, can be described using period and frequency, where period is the time to do one cycle of motion and frequency is the number of cycles per second. So to figure out that speed, it's 2 pi r over t, okay, or 2 pi f. And the reason why it's 2 pi f is because the relationship between frequency and period is 1 over t. So all I did for this is I substituted in f for 1 over t, okay? And then you can do a lot more examples or a lot more problems because you can also relate this back to that gravitational force. And so you can find the period of a satellite in motion. And this actually is from one of Kepler's laws of planetary motion. But again, basically what we're doing is we're taking that mv squared over r, setting it equal to gm mass of the planet over r squared, right? And solving this for t. Now, where does t come from? Well, t will come in this area right here, right? T is that 2 pi r over t, okay? So let's look at an example problem. And let me see, before I switch it over, I think we did an example problem using a swinging rope. So a person hanging on a rope. So we're going to see how tension affects this whole process here. All right, so you got a 35 kilogram boy swinging on a 7 meter long rope. He passes through the lowest position with a speed of 3 meters per second. What is the tension in the rope at that moment? Okay, so again, draw, sum, solve. That is our problem solving process. So we're going to draw our free body diagram. So remember, tension always points up to the point of application. Then we have the weight down. Okay, and this is the lowest point. So these are the only two forces acting at the lowest point. And something I failed to mention is that we always call positive into the circle. Okay, so even if we were doing that example with the roller coaster and we had Fn and Fg, right? These two would both point into the circle. So that would be our positive direction. So we have T minus Fg equals Ma. Okay. Then we just do some substitution. T minus Mg equals Mv squared over R. Still just, doing some algebra. So we add mg to both sides. So you get T equals, I'm going to do 2 steps in one. So I end up with mg plus mv squared over r. So m is common, right? So I'm going to pull that out. Okay, and then we end up with the equation T equals m times g plus v squared over r. And so now we can just plug in our values, right? So T equals the boy's mass, 35 kilograms. G, which is 9.8 or 10. In fact, when I did this problem, I called it 10. So I'm just going to stay consistent with that. Plus 3 squared, that is our speed at the bottom, divided by 7. Okay, and so something you're going to see, it's not going to add too much more than his actual weight because 3 squared over 7 is 9 over 7, which is just over 1. So what's inside there becomes 11 point something. And so T, the tension due to this, what's happening, is going to be 38.8 newtons. Okay, so this wraps up Unit 2. This is a dynamics unit, and this is one of those heavily tested subjects or units on the AP test. So just be aware that, this is going to be some of those harder questions, and we'll do a lot more example problems with it.